Okay, so let's look at this problem. The perihelion of Halley's comet is 0.586 astronomical unit, and the aphelion is 17.8 astronomical unit. AU is the Earth-Sun distance, which is roughly 100 million miles. Okay. Given that its speed at perihelion is 55 kilometers per second, what is the speed at aphelion? And so here's AU in meters, like I said, roughly 100 million miles. So what we are seeing is you may either use conservation of energy or angular momentum. So we'll use conservation of angular momentum as suggested. So here's the sun, and here's Halley's comet, and what conservation of angular momentum tells you is the following. If this is the location of the comet, there's the velocity, and m is the mass. The angular momentum is mv cross r, and this is constant. Okay. At aphelion and at perihelion and aphelion, so here it's going fast and here it's going slow. So velocity at perihelion, velocity at aphelion. At these points, the radius vector and the velocity vector are perpendicular to each other. So LP, again, L and the magnitudes are equal, and of course the directions are perpendicular to the plane coming out of the plane. But anyway, M VP RP equal to M VA RA. So what is it then? What's the speed at aphelion? So speed at aphelion is R perihelion, R aphelion divided by V perihelion. Okay, so I guess, yeah, we can put in the numbers right here. Velocity at aphelion, again, like we've said here, it'll be going slower, so it should come out less than 55 kilometers per second. And since this is a ratio, we can keep the units. We don't have to convert anything. Our perihelion is 0.586 AU divided by 17.8 AU times 55 kilometers per second. And this works out to 0.586 divided by 17.8 into 55, 1.81 kilometers a second. Okay, so what we have found is the Halley's comet at this point is going at 1.8 kilometers a second, and at this point it's going at 55 kilometers a second. All right, that finishes this problem.